Hello, welcome back. Um, Now venturing into 8.8 improper integrals. This will allow us to integrate infinite amounts of space and even integrate over discontinuities. Sometimes you can't do it all the time, but sometimes the amount of space can be basically fit into a box, and in those cases the integral will work. In other cases they won't. So if the integral works, they're going to call that convergent. If the integral doesn't work, they're going to call that divergent. Okay. So let's look at the types of animals we're dealing with here, sort of the zoo, if you will. The first one is the infinite integral. So you'll note, there's something new here. There's an infinity sign in our limit. And so they'll call that an infinite interval. And it literally is what you think it is. It's basically finding the area underneath this curve from 1 to infinity. Okay? Or at least they're trying to find that area. Maybe that exists, maybe not. And what other kinds? So you have infinite discontinuities, which are basically just seem to me to be infinite intervals on their sides, right? So let's say I'm integrating from 0 to 5 of 1 over x dx. That picture is basically just this thing flipped about the line y equals x, right? So except I'm starting at 0 this time, and I'm going to 5, right? So it's all of this space all the way up to whatever. Okay. So maybe it's not exactly this idea flipped, but you get the idea. We're trying to get all the area in here. Like up here, we're trying to get all this area. Okay, well, I'll shut up. Other types, you can have combos of both the infinite interval and the infinite discontinuity. This thing's an infinite discontinuity. Infinite discontinuity. This guy obviously isn't as identifiable as this guy in the wild. This guy has a big red flag sitting there. This guy, you can tell it's a discontinuity because within these limits, this thing will be discontinuous, which usually didn't happen back in the day. All right. What else? Yeah, so we can have combos of these guys. We can have both an infinite discontinuity and then an infinite interval on top of it. We could have two infinite intervals, kind of. So from negative infinity to infinity. And what you do with these characters is kind of just break them into two at some particular value, a to infinity. And there's obviously a discontinuity here. Let's clean that up and maybe look at some other function, right, that doesn't have a discontinuity. Let's say just 3x or something, right? So in that case, I could break it at 0. Consider this first infinite integral, and then consider this other infinite integral. And that'll be the approach. So we'll teach you the methods for dealing with these cases, and then when these cases happen, when you have two infinite types mashed together, you'll just break them down into the types where there's only one infinite discontinuity to deal with. Likewise, the same for having a discontinuity within an interval. So let's say I'm going from -1 to 1, something like, I don't know, something with a, let's go from, yeah, sure, -1 to 1 of 1 over x dx. So there's an infinite discontinuity at 0. So what they'll do is break it like this at that infinite discontinuity. Okay. So 0 to 1, 1 over x dx. Okay, that's the idea. The way it's going to be handled is with limits. So what you'll do is just replace the bad sort of limit on the integral with a variable, do an indefinite type, and it's kind of indefinite, but not really. You'll evaluate the integral, so it'll be more of a definite integral. And then you'll take the limit with that variable going to whatever bad place it is. Right? So let's look at it. Okay, so this is number 17. Hopefully this won't be very painful. So the big red flag here, we have this infinity. So that's bad news. We need to do something. And what we're going to do is kind of just drop it and replace it with a variable. Right? So you can use any variable you want. I'll use b. So now I have an integral from 1 to b. And then to kind of work with this infinity, I'll take a limit of this thing as this thing goes to this thing. Right? So limit as b goes to infinity of this integral. Right? Then what you're going to do is just basically forget about the limit for a bit and integrate this thing. Okay? So we can handle that. We learned how to integrate a lot. This is the same as x to the negative 3. So it's basically just the integral of x to the negative 3. We could do a power rule there. So it'll end up being x to the negative 2 divided by negative 2. And we have to remind ourselves to evaluate from 1 to b. I'm going to rewrite it just so it's more palatable. So I have negative 1 all over 2x squared from 1 to b. And then I'm going to evaluate that on my limits. Rather call these things bounds because we already have this limit out here. So in the future, I'm just going to call these bounds, okay? All right, so I'm putting the bounds in this integral. So plug in b, you get negative 1 all over 2b squared. And then subtract this thing evaluated at 1. All right, so minus negative 1 all over 2 times 1 squared is just going to give you 2. Okay. I'll clean that up a bit, and then you can start worrying about the limit of that thing. Right? So we'll end up with the limit of negative 1 all over 2b squared plus 1/2. Okay. Okay, so if you plug b into this thing, it'll be L all over infinity. And that type is 0. Okay, so if you think about sequences, you're putting in values of like 10, 100, 1,000, and for b. So it's going to be 1 all over something huge. And 1 over something huge is very small, is very close to 0. So this thing will zip away to 0, and you'll just be left with 1/2. Okay, so you can find the integral of this thing, 1 over x cubed, and from 1 to infinity. It has an area you can think of. And when this happens, you'll call it convergent. Okay. Let's move on, look at another one. Let's see what I got in my notes. So there's some slim pickings here for me. Here's number 19, the integral of 1 to infinity of 3 all over the cube root of x dx. All right, so big red flag there, so get rid of that. Replace it with a limit. Okay, I'm going to rewrite my integrand as 3x to the negative 1/3. And then you just kind of figure out this integral. So the integral of 3x to the negative 1/3. We have a 3 there. X to the negative 1/3 plus 3/3 is 2/3. Dump that guy in front. Remember to evaluate. All right, so that'll equal the limit as b goes to infinity of 9 halves x to the 2/3, and we're evaluating from 1 to b. That'll be the limit as b goes to infinity of 9 halves b to the 2/3 minus 9 halves 1 to the 2/3, so just minus 9 halves. Okay, so finally then this is the thing we want to take the limit of. Unfortunately, this object here will go to infinity, right? So b to the 2/3 is some sort of thing that's just going to grow and grow and grow. You can imagine putting in 10 to the 3 halves, 100 to the 3 halves, 1,000 to the 3 halves. It's just going to give you a sequence of numbers getting huge. So it's infinity minus L form. That's determinate. The infinity tells you where it's going. It will go to infinity. Okay. When you end up with infinity from your limit here, it's going to be divergent. And sometimes we'll be splitting the integrals. So even if the integral gets split and something is equal to infinity, they're going to, by definition, call it divergent. Okay, you look that up in the book. It's just the definition. I have not investigated it any further. I don't know if when you have infinity plus or minus infinity, maybe you have to do something else. I don't know. The book is just telling me to go with divergent as soon as you see an infinity symbol pop out somewhere. And that's what I do. Okay, I don't overthink it. So let's look at a nasty one here. I'm almost getting shaky thinking about it, right? Here's 21. Oh no, it's going to be hard. Yeah, anyways, negative infinity to 0. We have x e to the negative 4x dx. Right? So big red flag here is the negative infinity on the bottom side. So I need to replace that with a b. And then the limit as b goes towards whatever the heck that thing was. So we're going towards negative infinity. Okay, and then we have our integral. Apparently we'll have to do by parts on that character. Okay, so I need to evaluate this integral. To do that, I need to do by parts. So u and dv. Liate, so algebraic before trig. So algebraic for u, and then trig. Integral of e to the negative 4x is e to the negative 4x, and there's a constant of negative 1/4 floating about. And then the derivative, the differential of u is just dx, 1 dx. Okay, let's box that junk off. Right, so our integral will become this times this minus the integral of that times that. Okay, so negative x e to the negative 4x all over 4 minus the integral of this times this will become plus 1/4 times the integral of e to the negative 4x. Again, is just e to the negative 4x over 4 times negative 1. So it's integral, and I just want to cut to the chase because this problem is going to be long enough. Negative e to the negative 4x all over 4. Let's go ahead and clean that up a bit. We got to remind ourselves to evaluate as well. So what do we have so far? We have the limit of this thing, and this thing right now is negative x e to the negative 4x over 4 minus e to the negative 4x over 16. Okay, I need to go from b to 0. Okay, so let's plop that material in. And we get the limit as, and might as well tell our reader where we're going, b to negative infinity. Okay, so this thing evaluated, we put in 0, this is 0, minus 1 over 16, and then minus this thing with b in it, So you'd have negative b e to the negative 4b all over 4. And then this thing with b in it is negative e to the negative 4b all over 16. Okay. You can clean that up a little bit and start dealing with whatever the heck's going on there. This will be the limit as b goes to negative infinity of negative 1/16 plus b e to the negative 4b all over 4 plus e to the negative 4b all over 16. This thing is just a constant, so it'll go to the negative 1/16. This part will go to infinity. So the problem is you're putting in negative numbers into a negative exponent. So it'd be e to the negative times another negative at each point in your sequence. So, you know, e to the 40, e to the 400, e to the 4,000. If you're putting in negative 10, negative 100, negative 1,000. So this part seems to be going to infinity just by itself. Okay, so this is some constant L plus something plus infinity. Where the heck is this thing going then? We need to kind of figure that out. And you can do some inspection here, just sort of extracting it and taking its limit. What this thing is doing. So if you put negative infinity into this exponent, you also will have this infinityism going on. The issue, though, becomes when you multiply it by this b at every point. So you would have negative 10 times e to the 400, or sorry, negative 10 times e to the 40, negative 100 times e to the 400. If you put in negative 10, negative 100, negative 1,000, right? So in your sequence of values, it's getting really, really big negative. In other words, this thing is going to negative infinity. Okay? So that's kind of an issue, because if you have infinity of one type and then infinity of another type, it's considered indeterminate. Okay? So you're going to have to deal with this in some other way, rather than what we've done. So what I'm going to do is combine these two guys into one term. Okay, so this is equal to the limit as b goes to negative infinity of negative 1/16. If you have a negative exponent, it's really in the denominator. So really both of these guys have e to the negative 4b in their denominators. And then to get a common denominator, all I'm doing is multiplying this top and bottom by 4. Okay, so what? I'm going to go plus 4b plus 1 all over 16e to the 4b. Okay, so why do that? It's because now this thing right here is considered infinity over infinity. Okay? Or rather, well, no, that's not even accurate. That's if you put negative, yeah. So this, I mean, it won't be a L'Hopital thingamajig. Excuse me. Geez, it's still kind of a mess, isn't it? I was hoping I could do L'Hopitals, but I don't think I can. Let's rewrite this as 4b plus 1 times 1 all over 16e to the 4b. Okay. Now, what are these things? So as b goes to negative infinity, this thing will go to negative infinity, okay, this first part. The second part here, if b is going to negative infinity, this thing will go to positive infinity. Okay, I think we're getting somewhere now. This is a determinant type. If you multiply infinities together, you just get infinity. In this case, you get negative infinity in particular. So ultimately, the form here is L minus infinity. That's what this thing is. Okay. So at the end of the day, it'll just be minus infinity. In other words, it's divergent. Okay, so more of the story, these things can be very taxing when they start throwing in every little thing you've learned along the way. All right. Let's move over to, I guess, infinite discontinuities. No, we still have the doubly infinite type. So I have two infinite intervals kind of embedded in one integral. So 27, we have the integral from negative infinity to positive infinity of 4 all over 16 plus x squared dx. Okay, so the deal with these, if you have two infinity signs, you're going to split it into two integrals. Okay, so I'm going to do it like I'm doing arithmetic back in grade school. I'm going to have one integral here from 0 to infinity of 4 all over 16 plus x squared dx. And then add that to the other integral from negative infinity to 0 of 4 all over 16 plus x squared dx. Okay, and then hopefully I'll have my answer. Okay, if either integral is infinity, you're done. It's divergent. Okay. Okay. So anyways, let's do this guy. I need a limit as b goes to infinity of the integral from 0 to b of 4 all over 16 plus x squared dx. This is an inverse tan, so the a value is 4, the u value is just x, so that should be easy enough. I'll factor out this 4, and I'll get 4 times 1 over 4, which is just 1, times tan inverse of x all over 4. And then I need to evaluate that from 0 to b. Okay. So that thing will become the limit as b goes to infinity of tan inverse of b all over 4 minus tan inverse of 0. Tan inverse of 0 is just going to be 0. Okay, so I need not bother myself with any of that business. I'm just going to be taking the limit of this thing. Okay. So the limit of tan of b over 4. So I'm plugging in numbers that are getting bigger and bigger into tan. Tan inverse kind of looks like a cubic, but it has asymptotes at pi over 2 and negative pi over 2. Okay. So as the guts of the tan inverse function are getting bigger and bigger, the tan inverse function is approaching pi over 4, okay, or pi over 2, excuse me. It's the asymptote of tan. Okay, I want to do the same thing with this character. I kind of already know it's antiderivative, so I'm just going to skip to the chase, so to speak. This time the b value, of course, is going to negative infinity as opposed to infinity. And our integral then is tan inverse of x over 4, and we have to evaluate from b to 0. So this time we have the limit of, plug 0 in here, you get 0, and then minus tan inverse of b over 4. So it'd be minus tan inverse of b over 4. Okay. And then this just means the limit as b goes to negative infinity. I was not expecting this. There's something a bit odd. That I never noticed before. Sorry about this. Just never noticed it. Yeah. Well, anyways, b goes to negative infinity of tan of b over 4. So basically, negative tan is this thing flipped about the x-axis, and as b goes to negative infinity this time, negative tan inverse is going to pi over 2 again. Okay, so anyways, then pi over 2 plus pi over 2 is your answer. That integral is, believe it or not, pi. All right, so those are the infinite integral types. Now we want to worry about infinite discontinuity types. So let's move into that. Okay, again, you're going to deal with, you're going to attack these with limits. You just have to identify the discontinuity and sort of replace it with a limit, right? So 0 to pi over 2. of tan of theta d theta. Okay, so if you remember the tan graph, at pi over 2, there is an asymptote. Okay. Okay. One extra thing that we have to worry about is the approach. And basically, we're going to consider ourselves on this interval from 0 to pi over 2. And we're integrating inside the interval. Okay, so when I do my limit and I'm approaching the discontinuity at pi over 2, so as we'll say b goes to pi over 2, I also need to indicate the approach. Okay, so if you're you have to imagine yourself as standing inside the interval. And so if you're approaching pi over 2, you're coming in from the negative side. Okay. Okay, so you're going to put a little negative symbol there. That's really the only major difference between this and the infinite interval integrals. Okay. Okay, so here we go. 0 to b, tan theta d theta. Let's box all that junk off. Then that's equal to the limit as b goes to pi over 2 from the left. The integral of tan theta, of course, is ln absolute value of secant theta. Need to evaluate that from 0 to b. Okay, so that'll equal the limit as b goes to pi over 2 of ln absolute value of secant of b minus ln absolute value secant of 0. Smush that in. The secant function is just going to be 1 over cosine, right? So if you remember what that looks like, it looks like this. Okay. So it too will have this asymptote issue as it approaches pi over 2 from the left. So these secant values as we approach pi over 2 are going, 10, 100, 1,000, a million. It's just getting really, really big. And then you're taking the ln of those numbers, right? So the ln of an increasing sequence of numbers is going to go to infinity as well. The natural log function as x goes to infinity also will go to infinity. It don't seem like it, but it's just creeping along ever so slowly towards infinity. So this portion will be infinity. And then minus whatever the heck this thing is. Secant of 0 is 1, ln of 1 is 0. So it's just going to infinity, and therefore it's divergent. Okay, let's look at another. This is 35. So the integral from 0 to 2 of 1 all over the cube root of x minus 1. Yes. Okay, so what's the deal here? You don't necessarily see the discontinuity. Where is the discontinuity? That's where this thing has 0 in the denominator, right? And that's going to happen when x is 1. 1 is inside that interval. Right, so here's our interval. Here's our integrator person waiting to do his job. But sadly, there is an issue right there at 1. Okay, there's a discontinuity there. So what they're going to do is split it into 2 integrals, and you'll have basically 2 men to do your job. You'll be approaching, for this guy, he's going to approach from the left. For this guy, he's going to approach from the right. And that'll do it. Okay, so first, split up your integral. And again, I'm going to do it like, well, here, I'll do it here first. So 0 to 1 of x minus 1 to the negative 1/3 dx. And then plus the integral from 1 to 2 of x minus 1 to the negative 1/3 dx. Okay. So I'll do each integral separately. I need a limit to pull this off. So the first one, I'm coming in from the left. Okay, so I'm going to do a limit as b goes to 1 from the left of the integral from 0 to b of x minus 1 to the negative 1/3 dx. Right, and then my second limit plus the limit as b goes to, now this time I'm coming in to 1 from the right. Okay, so limit as b goes to 1 from the right. of the integral from b to 2, right, of x minus 1 to the negative 1/3 dx. Alrighty then, I need to integrate these characters. So the integral of this character, add 1 to the old exponent, divide, of course. You don't need a u sub. Okay, there won't be any constants to worry about. So you end up with the limit as b goes to 1 from the left of x minus 1 to the 2/3 times 3/2, right? So x minus 1 to the negative 1/3 plus 3/3 is 2/3, and then you plop that down in front, and we evaluate from 0 to b. So this will be the limit as b goes to 1 from the left of 3/2 times b minus 1 to the 2/3 minus, if you put 0 in here, it'll be 0 minus 1. Minus 1 squared is 1. 1 to the 1/3 is 1. So you just get minus 3/2. Okay. This thing is going to go to infinity. So you can imagine putting in numbers like 101 to the 101, yeah, so 102, yeah, 102, and then, you know, or 101, you get 101 minus 1 is 100 to the 2/3. Sorry, I just had a brain malfunction. 1001 minus 1 to the 2/3. So you just make them bigger and bigger and bigger. And this thing will go to infinity, and it'll be minus some number L. So this is infinity. And what I was saying before, as soon as you get an infinity, you're done. This thing is divergent. There's just no sense in going on with life. Okay. All right. And that's just definition. By definition, it's divergent. Look at the book. All right. So let's look at, I guess, can you look at it? Sure. Let's look at 43. So the integral from 3 to 5 of 1 all over the square root of x squared minus 9 dx. Okay. The discontinuity is at 3 this time. Some Mr. Integrator is going to be coming in from the right. So I end up with the limit as b goes to 3 from the right of the integral from b to 5 of this thing, whatever it is, 1 all over looks like a x squared minus 9 dx. I feel like I need to do a secant sub. And that's what I'm like, oh my gosh, really? I picked the wrong integral today. So x is equal to 3 secant theta. Dx is equal to 3 secant theta tan theta. Get your triangle, so secant theta equals x over 3, so theta equals secant inverse of x over 3. Do your triangle. So secant is 1 over cosine, so it'll be hypotenuse all over adjacent, and then the square root of x squared minus 9. Okay. So x squared opposite, this is just going to be tan of theta, so its limit as b goes to 3 positive of tan of this angle is square root of x squared minus 9 over 3. Okay, so this then I'm going to rewrite as tan theta. Okay, Kat, thank you. Times, and I need to clean this up a little bit. Obviously, tan theta is, this thing is tan theta all over times 3. Okay, so anyways, this guy would be this over this. So this would be in the denominator and 3 would be in the numerator. And then I'm going to have to multiply n by 1/3 to get rid of that issue. So I need to tack in a little 1/3. You could do the straight substitution if you want. Sometimes quicker just to take advantage of the triangle. Okay, so times 3 secant theta tan theta. And then the tans go away, the 3's go away, and you're left with the limit as b goes to 3 from the right of the integral of secant, which is ln absolute value of secant theta plus tan theta. Okay. We need to evaluate that. I still need the back sub to get it in terms of x's. So using my triangle then, ln absolute value secant, again, is, you already know what that is, it's x over 3, plus tan is going to be square root of x squared minus 9 all over 3. We need to evaluate from b to 5. Jeez. Hoping I'm right. I don't really know because I don't have the stupid solution written out. B going to 3 of ln of absolute value of b all over 3 plus the square root of b squared minus 9 all over 3. Sorry, I have to put in 5 first. So 5 and then 5 squared minus 9 all over 3. So what is this? This is 25 minus 9 is 16. That's 4. 4/3 plus 5/3 is, so this is some number L. And then minus the ln of the absolute value of b all over 3 plus the square root of b squared minus 9 all over 3. And we're going to 3, right? So if I plug 3 into here, let's see if we could do it just via substitution. Get 1 here, and then 0 here, so ln of 0. So yeah, it's equal to, it's convergent, believe it or not. It's equal to the ln of the absolute value of 9/3, so ln of 3. It seems unlikely, but that's what I got. That's my story, that's what I'm sticking to. I have no idea. I don't even have the solution anymore. Okay, great. So there's that one. Is there anything else I need to look at? Not really. Yeah, so we want to lead into working with series. Eventually in chapter 9, that's the next chapter coming up. So we have problems like 49 being thrown at you in the book, 1 over x to the p dx. And the reason why we care about these is the relationship to these guys. I guess n equals 1 to infinity, 1 all over, so what do we want to go? N to the p. Okay. So these things can be seen as a sum of an areas of a bunch of little rectangles of base 1, right? So this would be, this part is the height of the rectangle. And then what is the base? Well, the base is just 1. Okay, so you can re-envision it as a sum of area. Of course, we already consider the integrals as area, so there seems to be a relationship between this and this. And it's even more solid once you think, well, this curve has heights of rectangles based off of this formula. So the heights, and over here, the heights of the rectangle are based off this formula. So there seems to be this direct connection between the area underneath the curve and the area of these rectangles, and it turns out there is. Okay. Okay, so basically you could say that this adds up to something so long as this adds up to something. In other words, this is, if this is convergent, and that'll be the deal. Okay, so we'll look at classes of functions and sort of designate them as certain types, and we'll know that they converge or diverge based off of their exponent in this case. Okay, they'll be called P series, right? Okay, so I want to analyze this thing, and there's 2 cases in the beginning. You can always integrate with the power rule except when p is equal to 1. So you need to consider p equaling 1. So in that case, you have the integral from 1 to infinity of 1 over x dx. and replace limit as b goes to infinity of the integral of 1 to b of 1 over x dx. And then you have the limit as b goes to infinity of ln of the absolute value of x from 1 to b. And then that'll be the limit as b goes to infinity of the ln of b minus the ln of 1, which is 0. And then as b goes to infinity, the ln of b goes to infinity. So when p is 1, the integral is divergent. Okay, so let's do p not equal to 1. So when p is not equal to 1, you can split, you can do a power rule. Right? I can just add 1 to the exponent and divide by the new exponent. So anyways, let's put it into its limit form, going b to infinity of the integral from 1 to b of x to the negative p dx. Do a power rule on that character, so I have the limit as b goes to infinity of x to the negative p plus 1. I'm just going to write 1 minus p though, right? All over 1 minus p, and we are evaluating from 1 to b. Plop your bounds into that limit, so I have a limit as b goes to infinity of b to the 1 minus p, all over 1 minus p, minus 1 to the 1 minus p. 1 to any power is 1, so I just put 1 all over 1 minus p. Okay, so when p is not equal to 1, whether it's convergent or divergent is dependent on this term right here. Okay, so I claim then there's two cases to consider now here. There's the case when 1 minus p is less than 0. Okay? In other words, when p is greater than 1. And then there's going to be the case when 1 minus p is greater than 0. In other words, when p is less than 1. Okay? There'll be these two cases. And I'll just show you an example of the limit. So consider the limit as b goes to infinity of something like b to the, if p is greater than 1, we'll say p is negative. Let p be equal to negative 2, right? So b to the 1 minus negative 2 would be 3, all over 3. And then clearly this thing goes to infinity, right? It's a cubic. It's going to zip off to infinity. So my guess is that when p is greater than 1, it's divergent. And that turns out to be true. Okay. Let's look at this case and consider test value. So let p equal positive 2. Oh, so we screwed that up. We did the wrong ones. Crap. This is greater than 0, and then this would be less than 1, right? Okay, and then we'll make this less than 0, and this one is greater than 1. I apologize. That was a crap now, too. This is 1 minus p is, well, I want p to be greater than 1, so 1 minus p needs to be less than 0. Okay? And then over here, this was 1 minus p greater than 0, so p is less than 1. Okay, just in case you can't read that, there it is. Future generations will be able to behold the genius without me being there, right? Anyways, let's figure out the limit in this particular case. So consider the limit as b goes to infinity of b to the 1 minus 2, right? 1 minus 2 is negative 1, all over negative 1. I have a negative exponent, so I could drop that down to the denominator, limit as b goes to infinity of 1 all over negative b. And then in this case, it's L over infinity, right? L over negative infinity, but L over infinity nonetheless. In those cases, it goes to 0, right? So in this case, it's convergent. We suspect. We haven't proven that, but it turns out that that would be the case. Okay, so if p is less than 1, it's divergent. If p is greater than 1, it's convergent. If p equals 1, it's divergent. Okay. So we'll be looking at that kind of analysis in Chapter 9 and trying to figure out whether these guys actually add up to something. If they do add up to something, you can use them to do approximations of crazy things that we can't kind of figure out without a calculator in any way. Okay. Alrighty then, thanks for watching.